Any questions? Your attention, please. Any questions? No questions? Everybody's okay? Okay. There's, I did go through some of the homework. There were a couple of rough spots, so look at the notes that I made on your homework. And always, as always, even if I mark it 1, it doesn't mean it's right. You go back and check your work against the solution, which I have emailed out. Okay. All right. So let's suppose we have a function of time, e to the bt, where v is complex. Used to this function if v is real, right? If v is positive, this is an exponentially growing function of time. If v is negative, it's exponentially decreasing to 0, right? So if v is real, the imaginary part of v is equal to 0. Then you get a function either that grows if v is greater than time, or that diminishes if v is less than. Okay. So let's suppose that v is complex now. So let's suppose the imaginary part of v is not 0. Then let's write v in this Cartesian form, where we have the real and imaginary parts of v spelled out explicitly. It's some complex number like this. Okay, now we have the product of 2 pieces here. This is pure real, but this is complex. The exponential of an imaginary number. In general, complex functions of complex variables are complex. So this is like what we've done before here. If u is greater than 0, it's exponentially increasing. If u is less than 0, it's exponentially decreasing. This is an oscillatory function. That's oscillatory real and imaginary parts. Okay, so you can have then, if this is a complex function, so let's take the real part of this. The real part of this function is this part times the exponential. The imaginary part So you now have a combination of exponential increase or decrease and oscillation combined. So let's suppose I look here, I want to let's plot the case where u is less than 0. Then I get the real part of e to the bt. How's it going to look? This part with u negative. How does it look? Yeah, it's decreasing like this, but it's oscillating. So I need to extend this so I can get a better idea what it looks like. So there's an exponentially decreasing envelope combined with oscillation inside of the envelope.
What do you mean by envelope?
Well, you can imagine, so if I had just plotted the cosine function has minima and maxima, if I draw it well, minima and maxima plus or minus 1. This envelope is decreasing the amplitude of the oscillation. That's what I mean by an envelope. You could kind of draw a dashed line here, which instead of being constant, is now decreasing in time. So this piece with u negative gives you that envelope, and this piece gives you the oscillation. Now let's draw, but because it's a complex function, I have to draw the other part, the imaginary part as well. And you may get to be good enough after you practice this to draw them on the same plot. But for now, probably better just to use 2 separate plots. If you draw them on the same plot, then say the real part would be solid line and the imaginary part would be dashed or something. Difference between them. Okay, so what does this piece look like? Yeah.
When it starts from the origin.
Yeah, that's right. Sine starts at the origin. Okay, but it still is going to have this decreasing piece to it, and so there's still a kind of an envelope, which is provided by the e to the u is negative, right? So e to the minus something t, which is a decreasing envelope in time. Okay,
Can I take a picture of that?
sure. Yeah, and also it's going to be on Zoom recording, right? I think my sketch is pretty good enough to give you an idea about what it looks like, right? You can make a more precise plot. This gives you a generic idea of what it looks like. That's all contained in this function for B complex. Now, we did the simple harmonic oscillator last class. We took the simple harmonic oscillator, which is the solution looks like this, right? The oscillation forever. No dying, no decay, because we assume in the simple harmonic oscillator there's no damping, there's no friction, there's nothing that removes energy from the system, so it just oscillates. The mass on the end of the spring just oscillates. Okay, so remember this equation. And I said yes. And then we had the initial conditions. General, that is, the initial conditions are just generally written as some initial position and initial velocity. And then we guess something of the form. And we found then that B for this equation, remember what we got? That's pure imaginary. So going back, that means that U over here, the real part of B is 0. So there's no dying, there's no decay function. It's just oscillatory. You just have the cosine omega t and the sine omega t. So at the end, by working through this is the general solution you get. Where omega is the square root of the spring constant divided by the mass. Okay, so let's plot B on the complex B plane, the complex plane. Real part of B, imaginary part of B. This was a guess. We substituted into this particular equation. We found these two values for B. Let's plot them on the complex B plane. Where are you? Yes.
It would be up W and down W.
Right. I'm trying to draw an omega here. You need to, by the way, practice your Greek letters. They're used all the time. You just run out of letters. Just have the Roman letters. So physicists have incorporated Greek letters and other things. Mathematicians too. Okay, so plus I omega. So notice that there's no real parts to B. There's two numbers on the positive, negative, imaginary axis. Okay. So that's where we were at the end of the last class. And now I'm going to do a little bit more interesting problem where we get solutions that look like this. They come about because there's damping in the system. So I'm going to go back, modify this equation. Instead of doing the simple harmonic oscillator, I'm going to do the damped harmonic oscillator. I'm going to put all the terms on the left-hand side. So I can put a 0 here on the right-hand side. So this is a new term compared to that one. this is a viscous force. It's proportional to the velocity. So it's always opposed to the velocity, and it will always remove energy from the system. Then we expect to get that kind of behavior, damping. Let's go through this trick again, just to get our exercise, the complex numbers, and how they can be used. I'm going to substitute this yes into this equation. See what happens. Okay, the first derivative is the v. Second derivative is the v squared. So I can factor x out. So this becomes mv squared plus gamma v plus k times a to the bc. So I've converted, once again, converted the differential equation into an algebraic equation. So it's sufficient for me to solve this algebraic equation for b. And that gives me, again, there will be two roots. Over here, we had two roots, plus and minus omega, which combine to give sine and cosine. Now we're going to have a complex values for b, but they're going to have it, b is going to have a real part to it. So I've got a damped behavior. So let's use the quadratic equation. Solve this for v. So gamma minus gamma plus or minus gamma squared minus 4km 1/2 over 2m. Okay, so now the first thing we need to do is to recognize that discriminant there tells us about the character of what's going of the solutions. If this discriminant is positive or negative, we'll get different solutions, different kind of solutions. So let's look at the case where the discriminant is negative. Let's look at that first. So the discriminant here is gamma squared minus 4km. It's less than 0. Let's do this case first. Okay, so, and that means that gamma is less than 4km. In other words, this corresponds to weak damping, or also known as underdamped. There's obviously a critical value there. Gamma is equal to square root of 4km. And there's something special going on at that point. That's called critical damping. If gamma is less than that critical value, it's underdamped. And now we can see here, if this is negative, then we have B is complex. Okay, so now I can pull out a negative sign from the discriminant, and then the square root of -1 is I. So I can write this where this is real, and then this is real. So in other words, B is now complex, both real and imaginary parts. The real part is negative. So what does that correspond to? That tells you. Yeah, this is the real part of B, which means it's exponentially damped. Not exponentially growing, right? Because the real part is negative. So the system is always going to lose energy, never gains it. And this part is pure imaginary, which corresponds to the oscillatory part. Oh, I need to divide by 2 in there. Excuse me. So this part, you could rewrite this part 4km minus gamma squared over 2m. You can take the 2m squared, put it inside the square root, and you get square root of k over m minus gamma squared over 4 inches. Okay, here's that old frequency that we had before when there was no damping. If gamma goes to 0, we get back to the result we had before. But now you can see that the frequency of the oscillations is shifted slightly by the damping. It's oscillating at a lower frequency than it did before. So the damping has an effect of stretching out the oscillation and also dampening. Okay, so let's plot these two roots on the complex B plane. And be careful here, by the way. Don't get confused. I'm writing this on, I'm going to plot B on the complex B plane. We're also making a plot of x of t, real and imaginary parts, possibly real and imaginary parts, right? So we've got two different complex plots going on. Don't get confused. You got to sort that out in your mind. Right? I just demonstrated a plot of e to the bt, where e is a complex number. That was a function of time, had real and imaginary parts. This is a different plot, although it's complex also. It indicates the roots of the solution. Okay. All right, so now where do these, there are two of them. Where do they fall? The imaginary parts are opposite to each other, but there's a real part which is negative. So where do they fall? So over here, real part is negative, and they're straddling the real axis. They were on the real axis, and now they're shifted to the left, and they're closer to the real axis. So to compare them to what we were getting before, these are coming down like this as a function of gamma, as a function of the damping. These are coming down, approaching the real axis, so on the left, as a function of gamma. So here's where gamma is 0. We've got these two roots. And then for gamma is less than 4 km, it's someplace along this arc. Two of them. Maybe I should dot this so you can understand that there's a range of possibilities that you can control the damping on the system somehow. Increase the damping. Then you're moving the roots down this way. Okay, now if the discriminant is equal to 0, that would be case 2. The damping is right at critical value. Gamma is equal to root 4 km. Imaginary part's gone away. So you're right there. Okay. So there's no oscillation taking place anymore, right? This has two, it has a complex value B, so it's got damped oscillation. So both the cosine and the sine parts are damped. So that corresponds to the mass on the spring is just slowly losing its energy. Okay, but now we've raised the damping enough that we get critical damping. There's no oscillation left. And so the system will behave, no oscillation. So x of t, you get a complete solution, it just does this. Asymptotically approaches. It never really reaches it, but it does not oscillate. Okay. So this is critical damping. There's one value of the damping coefficient that will cause it to be critically damped. Okay, finally, case 3. Gamma is greater than the critical value. What happens to B now? The discriminant is positive. real. Here are two real roots. Let's plot them on the complex B plane. Right here and right here. That's called overdamped. So this is underdamped, this is critically damped. And this is overdamped. Overdamped. It's let's see. It takes let's see, it goes, yeah, it goes, I think, if I remember correctly, let's see, it may actually shoot over once like that. It's losing energy faster, but it can overshoot, but only once. So critically damped, if you're trying to get rid of the energy without having any oscillation, you want it to be exactly critically damped. The system will just die out without oscillating. Okay, so this is a way of characterizing the solutions to this system, the damped harmonic oscillator. And you're plotting, again, to remind you, on the complex B plane, where B is the coefficient in the exponential. In general, B is complex. If it has imaginary parts, then it has oscillatory character. If it has a negative real part, then it's dying, it's decay. And so you can see the whole picture here, how the system works by changing these parameters, the mass, the spring constant, the drive, the drag. Yes, ma'am.
Sorry, is the two x's that are on the real axis, those are the ones from the overdamped
Yes, ma'am.
version?
That's right. Mhm. The discriminant is positive, so you have two real values here. Yes, sir.
What does underdamped look like graph-wise?
Underdamped is what I drew originally. Underdamped will have this. Damped cosine and a damped sine. That's underdamped. It's oscillating. So the damping has not removed the oscillation.
So that's a good thing. Or
What else do you want? You want it? I don't know. It's good.
yeah, yeah.
Nature is wonderful, right? But I'm not sure what you mean by good. Depends on what you. If this is a shock absorber, you don't want this. Right? Because the car is going to keep on rocking after you run over the bump. You want it overdamped, at least, or at least critically damped. So this is a shock absorber. You want something around here. Right? You get that? Oscillations in the car are bad. You don't want it to the whole car rocking because the shocks are not strong. The shocks don't have enough damping in them. So the car will just rock. That's something's wrong with your shocks. Does that make sense? Questions? This is a beautiful example of using complex numbers to solve complex variables, to solve some simple physical problems. These equations show up again and again and again in physics. If you keep taking more advanced courses, you'll see these equations again, and you'll be able to do this again. So practice this. This is really good for you. Get to know the simple harmonic oscillator and the damped harmonic oscillator. Then you think of other physical systems which are governed by similar mathematical equations. Yes, sir.
Tides.
Say again?
Tides.
Tides.
Dr. Myers going
Yeah, it's
in
true.
factory sciences. We did this just like yesterday, I think.
Yeah. So there's an underlying oscillatory system, but there's also the drag.
Right.
Yeah. So that's a little complex, but it's true.
Say like a pendulum with drag or
Pendulum with drag.
or the stereotypical spring.
Right. Yeah. So the focal pendulum downstairs has damping in it. We have to keep pumping it. That's the part that's missing from this. If there's an applied force that keeps it going, then that would have to be added to this. But if you turn off the damping, the driver, the focal pendulum downstairs has something that keeps it going. You don't see that, it's not obvious in the setup, but it's got to be there. Turn that off, the pendulum will swing down to nothing. It will be an example of underdamped. Damping is weak. How about from electronics? E&M. Remember we did this in E&M.
Oh, yeah, the one the current, the speed, the current, or when it goes through the wire, it reaches a max, right? Or, I'm sorry.
Was it? Discharging the capacity.
Yeah, there you go. Let's discharge a capacitor through a resistor and an inductor. Let's do it first without the resistors. We have a capacitor, we have an inductor. We charge the capacitor and then allow it to discharge through the inductor. Circuit equation is this: for Q is the charge on the capacitor. Right there. And engineers, electrical engineers, will talk about the complex. They'll use phasors to solve this differential equation. Talk about the response of the circuit. So they're doing this. All right, what if we put a resistor in here? We've added another term, which is proportional to the current flowing through the resistor. That's the damped harmonic oscillator. So the resistor is providing the damping on the system. And now we'll get this behavior. If the resistor is not very strong, we'll get underdamped. If we put a stronger resistor, we're going to get critically damped or overdamped. So the charge on the capacitor is going to look like this.
And for critical damp, it bumps a little under, but it comes back on top.
Yeah. No, it doesn't come back on top. It never goes down below and comes up from below.
One solution, right?
It depends on the initial condition. So I can't sketch it
Yes, sir.
because you have two initial conditions, position and velocity. So I can't give you something that works in all cases without taking more time. But the overdamped tends to overshoot once only. It comes up from below. But it does depend on the velocity, initial velocity. Okay, this is going to keep cropping up. This mathematical equation will show up in lots of places. Wherever there's a restoring force, bringing something back to some kind of equilibrium point, along with the drag, possibly some kind of damping, so it loses energy. This is you're going to see it over and over and over. Quantum field theory is this. I mean, harmonic oscillators that are interacting with each other. Okay. So you should spend time, get to know this harmonic oscillator and the damped harmonic oscillators. You should be able to solve it in about 3 or 4 different ways. And so you should be on the lookout for that, learning those different ways of solving the simple harmonic oscillator, damped harmonic oscillator. And then the last piece is to have a driver, have a driving force. So that would be the last part of damped driven harmonic oscillator, the thing that you see everywhere. Okay, so all right, so plotting oscillatory functions. Cosine and also sine. There's this thing in there called the frequency, omega. It's angular frequency. Called angular frequency because omega t looks like an angle. So if omega t is in radians, then what is the dimensionality of omega?
1 over seconds.
Yeah. Radians over seconds. So radians are technically not ordinarily, instead of degrees, or cycles per second. So angular frequency is in radians per second. Radians per time. So if omega t, if this is cosine omega t, starts off at 1 for t equals to 0, when it comes back to its full value, that's called a period. I'm going to call it capital T. What's the relationship between omega and capital T? The angular frequency and the period.
1 over?
Almost.
Oh, 1 over the actual f, so you got the 2 pi in there.
Now we want omega T to be 2 pi, right? Because cosine goes from 0, cosine of 0, all the way around the circle, all the way around back to 2 pi, returns back to its initial value. So the period is 2 pi over the angular frequency, or the angular frequency is 2 pi over the period, whatever way you like to do it. This is the relationship. So you'll also see nu, which is omega over 2 pi. This is also called frequency. And the other one is called specifically angular frequency, to make sure that you understand the difference between the two. The dimensionality of frequency is cycles. And this is hertz. Cycles per second. Hertz is in cycles per second is 1 hertz. 1 hertz is 1 complete cycle, and it takes 1 second. Yes, ma'am.
Do some people use f for that?
Yes.
Okay.
Yep.
I've never seen the v.
Some people use that. Physicists tend to use nu. Doesn't matter. Whatever symbol, just know what your symbols mean and be consistent. And generally on homework and tests, just tell me what your symbol is, right? You can make up your own symbols, but you got to tell me what they are. Otherwise, I have no idea. I'm just guessing. Okay, so that's for a function of time. By analogy, let's suppose we have a water wave, which is moving. Let's take a snapshot. Get out the camera, take a shot, picture of it. Now it looks like this, but it's not. It's how it's arranged from one part to another. So we get a similar sort of behavior as a function of x. Again, there's a cosine-like piece and a sine-like piece, which are independent of each other. The complex exponential combines both cosine and sine parts together in a very compact way, right? Because of the Euler relation. There are always 2 different independent parts, the cosine and the sine part, and expressing wave-like character. Okay, so now we're talking about the distance traveled going from one peak to the next peak. That's called the wavelength. This distance is the wavelength. So the wavelength is like a spatial period. Okay. Now, what's the other part here? There's something that's like a spatial frequency. Yeah, it's 2 pi over the wavelength. 2 pi over lambda. So don't get confused. We usually use K for this. Don't get confused with the spring constant. This is called wave number. Wave number is like a spatial frequency. Wavelength is 2 pi over the wave number. Dimensionality of K, just like the dimensionality of omega is radians per time. Dimensionality of K is radians per distance, per length. Spectroscopists talk a lot about wave number, and unfortunately, there's just like there is a factor of 2 pi comparing different ways of talking about frequency. There's also that for wave numbers. Some people have a factor 2 pi in there, some people don't. It's very confusing when you're trying to understand it. But spectroscopists will talk about wave numbers. or frequently when you're looking at lasers. Instead of expressing wavelengths, they talk about it in terms of wave number. It's just an inverse. Okay? All right, so just as there is a period and a wavelength in time, there's a period, period and frequency. In time, there's a wavelength and wave number or distance. We're now going to combine those because you know that watching a water wave is doing both things at the same time. You're in one place, you put a cork in the water, it's going up and down. So there's the time dependence that's oscillatory. But also from one place to another, there's an oscillation in the wave. We've got both things going on. So now we're going to develop a mathematics that operates in this both ways, both in terms of x and t. Okay, so I have a function like this. I want to study this as a function both of x and of time. So this is a traveling wave, a pure wave, in the sense that it has one frequency associated with it. And so it just oscillates forever, both in time and in x. Obviously, that can't happen. This has got to be some kind of approximation. You can't have an infinitely extended thing, right? But in some region, it can be close to this. Okay, so, well, how do you plot something like this? It's a little bit of a challenge. You could do it, if you can make a three-dimensional plot, you could plot this function. So you would have, it's kind of hard, say x and t, like this. Here's the function. How would you plot something like that? It's a little challenging. But you could do that. Maybe I didn't bring my computer, so I can't do it for you. But let's think about it this way. We just freeze it at some time. So we fix this value, and it's a cosine of kx minus constant. Use the double angle formula. So if we fix the time, we have cosine kx minus some constant. Use the double, the angle addition. We call it. So in general, it's a linear combination of cosine and sine in x. Okay. Now let's suppose we want to follow the crest. So this is going to have a maximum. Let's follow the crest. Yeah.
Wouldn't that be addition?
Oh, excuse me. Thank you.
Yeah.
So let's follow the crest of this function. So in other words, let's pick a point where the function is a maximum. And let's pick the point, let's suppose at t equals to 0. Where does the cosine reach a maximum? Well, it does at x equals to 0. Right? So there is a maximum at t equals to 0. This maximum at x is equal to multiples of 2 pi. Every 2 pi. So let's choose one. Let's choose the x equals to 0. And the function is 1. Okay, now what's going to happen at later time? That feature is always going to be there where the argument of the cosine is 0. So we can follow the feature. Follow the maximum with the argument ain't 0. Starts off x equals to 0. Where the maximum is at t equals to 0. At a later time, the maximum will occur wherever that combination is 0. So this is the position of the maximum that was at 0. It's now going to be at some later time going to satisfy this. So solve for x. X into omega over k. does that look like? That's just linear motion. The maximum is just sliding along, and the speed is omega over k. Remember the dimensionality of omega was radians per second, say, or per time. And the wave number is like the spatial frequency. So it's radians per length. So this is a length per time. The dimensionality of that ratio is like a speed. Omega over k is like a speed. Okay, so with this negative sign here, I chose this negative sign when I wrote it up here. Gives you motion to the right. Omega and k are both positive. And this is just traveling to the right. How about to get the left traveling wave? Yeah, I just put plus here. And it would swap the sign over here, so now it's traveling to the left. Left traveling, right traveling waves. Questions?
Minus sign is traveling to the right.
Minus sign here
Yes,
is traveling to the right.
thank you.
Comes up to be a plus here.
Make it double clear.
Plus sign here, assuming k and omega are both positive. Plus sign here would be a left traveling. So we're going to study waves like this, and the next thing I'm going to do is to introduce you. I'm getting a little bit ahead, I think 1 or 2 lessons ahead in homework, so don't panic. You'll have a chance to come back and review this. This is a solution to a particular wave equation. And we'll study that wave equation, which is appropriate for water waves on a very deep ocean. Doesn't work for waves coming in on shallow areas, like up on coming up to the beach. This wave equation doesn't describe that because the height of the wave is comparable to the depth of the water. The wave equation, excuse me, we're going to study it. It would be appropriate for water waves on a very deep ocean. So the wave's height is very small compared to the depth of the water. And you get a very simple wave equation, and that's what we're going to study. And this will be a solution to that wave equation. This is all preparing us to study the Schrodinger wave equation for quantum mechanics, which involves complex variables. Okay, so I have your tests graded here. Here are the solutions. So on your way out, let me hand these out. So don't move yet. Let me pass these out before y'all leave. It will help you to put names and faces together. I'm sorry to put you through this, but it's important to me to get to know your names and faces as best as possible. Under the circumstance. Are you smiling? I can't tell. Pick up solution on your way out.